Hello, this is the Retroviruses and AIDS Virology tutorial presented by the SchrDbb. We reference Lippincott illustrated review of microbiology by Cynthia Cornilesson, Bruce Fisher, and Richard Harvey. So here we are going to start with, you are going to visualize retroviruses and AIDS tutorial. So here it means you're going to start with the classification of retroviruses. Generally, an example is HIV virus, HIV. So we have RNA virus. Under RNA virus, we have single-stranded. So under single-stranded, we have positive and negative. So they are positive. So under positive, we have envelope and we have non-envelope. The retroviruses are envelope. Under envelope, we have icosahedral and helical symmetry. They are icosahedral. And under the under this RNA virus, under this retrovirus, we have icosahedral, we have Retroviridae, we have Flaviviridae, we have Togoviridae. We have already seen the Flaviviridae, we have already seen the Togoviridae. So here today we are only going to see the Retroviridae. Inside the Retroviridae, which are the retroviruses, you have the human immunodeficiency virus, that's HIV 1 and 2. Those are the two viruses. And you also have the human T-cell lymphotrophic viruses 1 and 2. And the human T-cell lymphotrophic viruses are also other lymphoproliferative viruses, which can cause malignancy such as lymphomas. So and leukemias. So we are not going to speak about that. So let's continue. So this is the structure of human immunodeficiency virus. So human immunodeficiency virus is made up of a central RNA. So this molecule here is the nucleoprotein. So you can see the nucleoprotein inside. That is central RNA. You have reverse transcriptase. You have integrase molecule on it. You have the major capsid. So we have two main capsid. You have one capsid inside, which is a major capsid, which is made up of the protein P24, and we have an outer capsid here, which is a minor capsid. You have an outer capsid, which is a minor capsid, and outer matrix protein, which is made up of the P17. Now, above it, you are going to have the envelope. So we have the envelope above like that, and the envelope is made up of different molecules. It's made up of the host protein. It's made up of the lipid membrane envelope that is derived from the host. That's one for the host protein. So you have lipid membrane envelope from the host that you have already seen. We have the transmembrane protein fusion that is made up, that is the GP41. So we have the transmembrane proteins, which is GP41, and we also have the surface proteins. One is the transmembrane proteins, another one is the surface protein for that's also called the attachment protein. The transmembrane protein is also called a fusion protein, that's GP41, glycoprotein 41, while the surface protein is also called the attachment protein, that is the GP120. So what is the structure of human immunodeficiency virus? So that was seen. Now this is the estimated population of the prevalence of worldwide HIV. Is it clear? So as you can visualize here, when you see it is this color, it means that it is more than 15%. You see the areas where there is high level is in South Africa and the countries around. The question is, why is it that South Africa is having this high rate of HIV? The answer is because the president of South Africa declared officially that HIV was a disease of the white. Is it clear? So it was a poor declaration of himself. He declared that the HIV was a disease of a white, and then it was not involving black people. So people were there continuously doing sexual intercourse without using condoms. Is it clear? Without protecting themselves. So that's why there is high rate of HIV, extremely high rate of HIV in this country. Is it clear? So you have to be very careful if you want to have any form of sexual contact with any person around here. So the next one is the highly active antiretroviral therapy introduced. So you need to know that after the introduction of highly active antiretroviral therapy, before in the past, you see how the incidence of AIDS was high, and you see how the deaths of AIDS was very high. You see the death from AIDS was extremely high. Is it clear? But now after the addition of highly active antiretroviral therapy, you see that the death cases have reduced drastically. Now this is the human immunodeficiency virus povidal genome. So this is the genome of the human immunodeficiency virus. You need to know that in the genome we have the binding site for host transcription factor. You are going to have the code for the capsid protein matrix and the nucleocapsid protein. You are going to have the code for the reversal transcriptase and the protease, the integrase and the ribonuclease enzymes. You're going to have the required, this is required for the HIV virion that promote the infectivity. Is it clear? And this is a transcriptional activator, this is a potent activator, and these are the other elements. This is required for efficient virion building, and these are the other elements. So you can pause and visualize all of them. So the binding of the human immunodeficiency virus is surface of the lymphocyte. So how does it bind? So at first the HIV virus comes with its envelope, and the envelope is made up of the transmembrane protein and the surface protein. Is it clear? So the surface proteins are going to bind with the co-receptors on the white blood cell, that is the CD4 receptor. Surface protein is made up of the and the transmembrane protein is made up of the glycoprotein 70 and glycoprotein 41, which are going to bind with this and cause now the release of the nucleocapsids into the cell. So how does replication occur? After the release of the nucleocapsid, you are going to have the release of the plus single-stranded mRNA. So is it clear? Now the positive strand single-strand RNA molecule is going to enter the nucleus because it's going to be a RNA-dependent DNA polymerase, which is going to produce DNA from this RNA strand. Is it clear? It's going to produce DNA. Now the RNA is going to be removed, and then the DNA is going to have its complementary pairing to produce a plus strand DNA and a minus strand DNA. Plus in DNA corresponds to 3' to 5', while the minus in DNA corresponds to 5' to 3'. Now it's going to be transported now to the nucleus. Is it clear? Via the enzyme integrase, going to transport to the nucleus, and then it's going to integrate it to the host genome. When the host genome is going to be integrated, now is going to the host RNA polymerase is going to convert the HIV DNA that has been integrated now to RNA. Is it clear? That's splice RNA and full RNA. Then the translation is going to occur at the level of the cytoplasm in the ribosome to produce the capsid envelope. Is it clear? And also the host RNA is also going to produce a viral positive stranded single-stranded RNA that can be assembled now with the capsid to produce the different HIV. Is it clear? But the different viral particles which now can be moved out of the host cells. Now this diagram here is to show the processing of GAG and the polyprotein precursor protein by the viral protease. So these are the unspliced viral mRNA. So with the unspliced viral mRNA, so you are going to have, so in cases where you have viral mRNA, you need to know that in 10% of cases translation is going to occur via the unspliced viral mRNA, while in 90% of cases you are going to have GAG protein precursors. Now in those GAG proteins also you are going to produce proteolytic processing. You are going to produce the proteolytic processing. You are going to produce the matrix protein, the capsid protein, and the nucleocapsid protein, while the GAG polyprotein precursor are going to do proteolytic processes to produce the reverse transcriptase and other enzymes. Is it clear? So you see that the enzymes of HIV are produced from the unspliced viral mRNA, which are directly translated by the flame shift translation. Is it clear? In 10% of cases. Why? Translation, normal translation, this is translation with frame shift, and this is translation without frame shift. If translation with frame shift occur, it's going to result to the reverse translation of other enzymes. If translation without frame shift occur, it's going to result to the different molecules of the capsid. Now, what are the common mode of transmission of HIV? The first and the most common one is sexual intercourse. If you are doing, generally there is a frequency rate. If you do sexual intercourse with heterosexual intercourse with an infected partner, there's a high risk for females compared to male. Is it clear? And the females is going to be something is 50 to 60%. Is it clear? 50 to 60% for females, and for males is 40 to 50% in males for you to have HIV with an unprotected sexual partner. Now, with homosexual partner, usually the rate is more higher than with heterosexual partner. In homosexual partner, the rate is between 60 to 70% of transmission of HIV generally. Now, transfusion is also another way of transmission of HIV. We have contamination of needles. Generally, contamination of needles, HIV, for you to have a spread of HIV via the contamination of a single prick is 1%. Is it clear? So generally, for you to have contamination via needle is only 1%. So if somebody have HIV and before you consider needle contamination, you must have excluded all of this. So perinatal transmission can be through intrapartum, so it can be antepartum through transplacental, it can be intrapartum during labor, and it can be postpartum during breastfeeding. So these are the different risks. In homosexual sex, it is 51%. Generally, when you do homosexual coupling, it is 51%. In heterosexual, it is 8%. So it is much more less than compared with homosexual sex. So this is another reason to tell you that homosexuality for me is not a good thing. So I'm categorical with that. So from here again, you can see homosexuality is not good. Basically. So the next is heterosexual sex is 8%. As you can see here, it is very less compared to homosexual sex, which is 51%. Now, injected drugs use is injected drugs in case when you are injected, it is 8%. Others is going to be so like in blood transfusion, it's in the case of 32%. Now others, you have things like 8% like the child. So when it's intraplacental, you need to know that when a mother has a high viral load, the transmission of a child with HIV so from the antepartum transmission of HIV to a child is going to be 15. Antepartum transmission of HIV to a child is going to be 10 to 15%. The intrapartum during labor is going to be 20 to 30%, and then the postpartum is 15 to 20%. So the highest percentage of transmission of HIV to the child is during labor, and then comes the breastfeeding, and then before is the least. So this is transfusion and other blood prick material. When you are being pricked is 1% and less than 1%. So when you have blood transfusion and you are being pricked by certain material is less than 1%. Now worldwide, you need to know that injecting drug abusers, when you take from one drug abuser to another, you are just sharing things, it is 5%. Is it clear? In heterosexual worldwide, so I was talking about worldwide, it is 70 to 75%, and homosexual worldwide is 5 to 10%. This value, I don't know why it has highly changed compared to this one, but I would prefer the USA value, maybe because of some modifications. And other, you have 0 to 17% in children, and then blood as that. Now the next one, we have typical cause of human immunodeficiency virus. So you need to know that you have in the course of the human immunodeficiency virus, start with primary infection, then you have a latency period, then you have AIDS. So at the beginning, you have for 2 to 4 weeks the primary infection, then 6 to 10 years the latency, and then 2 to 3 years later you're going to have AIDS. Then this is, so you need to know these are the different diagrams. So the diagram in green is going to show the CD4 level. The diagram in purple is going to show you the virus level in blood, and then the diagram in pink is going to show you the anti-HIV antibodies. So you need to know that what at the beginning the CD4 level is going to be very high, that is 1000. So that's the normal level of CD4, supposed to be 1000. So the viral level, so when you have a primary infection, the viral load is going to be extremely high. So when you are primarily infected for the first time, the viral load is going to be extremely high at this level, and you are going to have extremely low CD4 count. Is it clear? So later on, the viral load is going to reduce when the anti-HIV antibody is going to increase, and by that time when the anti-HIV antibody increase, you see the CD4 count is going to slightly increase. Is it clear? Now the virus in blood, you will not see any virus again in blood. So HIV, the detection of HIV is not by the presence of virus in blood. Is it clear? But it's instead by the antibodies of HIV in blood. That is how we detect HIV, not by the presence of the virus in blood, but the presence of the anti-HIV antibodies in blood. So when you have the virus, so you have the so here you're going to have flu-like symptoms at the beginning, but here you don't have specific symptoms. You just have flu-like symptoms at the beginning of HIV. so throughout the body, you can have fever, you can have cough, you can have catarrh, you can have joint pains and all that. So now so when the anti-HIV antibody increase, you have a decrease in the CD4 count. You have decrease in CD4 count. So when you have a decrease in CD4 count below 500, now it's becoming a problem. Is it clear? So when it's below 500, and now it's called, you can now grade HIV. HIV, when it is between 300, when it's between 400 to 500, is going to be mild. When it's between 200 to 400, is going to be moderate. When it is less than 100, is going to be severe infection. And you have also a classification with the viral load, and you have a different classification. Now with AIDS, it occurred 2 to 3 years after. So you're going to have here with AIDS, you're going to have skin and mucous membrane immune defect. Is it clear? So in this case, you see the anti-HIV antibodies in this case has reduced again, and then the viral load is increasing. So when the viral load at this point in time is increasing, it means that there is no compliance with so it means that their body is failing, is it clear, against HIV. By this time the patient is asymptomatic when you have the high level of anti-HIV antibody. So when you have high level of anti-HIV antibody, in this case you are asymptomatic but you are having HIV. So that's why many people may have HIV but they are just asymptomatic. Is it clear? So you see this latency can take a period of 6 to 10 years, very long period of time between them, because of this latency. Because if you can see, you have nothing in the viral load, but you can only have the anti-HIV virus. But later on, when it's want to occur, you have now low level of anti-HIV antibodies, and then the viral load increase, and then the CD4 count is also reducing. So now, in the next diagram now is a pathogenesis of human immunodeficiency virus. So after sexual contact, transmission, contaminated needle, perinatal transmission, you have HIV in blood. What happens is that you have macrophages now can release infectious virus over the long period of time without death of the cells. So what happens is that at the beginning it's going to infect the macrophages. So when it enters the macrophages are the ones that are going to first store the HIV for a long period of time. Then it's going to enter now it's going to infect the CD4 cells. In the CD4 cells, you are going to activation of CD4 cells. It's going to result to CD4 death. Is it clear? So lymphocyte replication release mature virion and result to death of the cells. and also have the persistent infection. The persistence of the infection is because of the macrophage, because the CD4 cells are going to be stored inside the macrophages. Is it clear? So they would say the macrophages are the ones that are storing actually the HIV viruses, but the ones that are suffering from the viruses are the CD4 lymphocyte. Now, in severe infection, you are going to have opportunistic infection. You can have Kaposi sarcoma, you can have lymphoma, you can have wasting syndrome, you can have dementia based on the classification of HIV, because HIV is classified into 4 stages. In stage 1, generally is asymptomatic. Is it clear? When you are in HIV Class 1, based on the clinical symptom, generally in HIV Class 1, it is asymptomatic. Is it clear? You can have some mild weight loss, but generally you have nothing. But in Class 2 now, you can have a weight loss of greater than 10%. When you have weight loss of greater than 10%, that's the first thing. Second thing is that you can have oral thrush, that's oral candidiasis. You can have herpes zoster. You have the herpes zoster. You have things like things like fever, febrile condition. That one is already HIV Class 2. Now HIV Class 3, you have things like esophageal candidiasis. You have things like pulmonary tuberculosis. You have things like local opportunistic infections. As I've said, you have esophageal candidiasis. You have pulmonary tuberculosis. You can have other skin infections. Is it clear? So other skin infection. And then now in the HIV Class 4, in HIV grade 4, now you have systemic opportunistic infection like cryptococcal meningitis. You can have meningitis caused by tuberculosis meningitis. You can have other systemic spread of the disease. You can have also in the HIV stage 4, you can now have cancers such as because there are 3 main cancers shared with HIV. The first cancer is lymphoma, the second cancer is cervical cancer, and the third cancer is Kaposi sarcoma. So those are the 3 main cancers shared with HIV. Is it clear? So the first is Kaposi sarcoma, the second is lymphoma, the third is cervical cancer. Those are the cancers that share with HIV. So now these are the opportunistic infection with HIV. See that? So at the beginning of HIV infection, the first opportunistic infection that come is the herpes and the candidiasis, just as I have said. So that's why in HIV Class 2, in Class 2 HIV, you are going to have herpes infection and you have candida infection first. Is it clear? So at the beginning, you have herpes infection, you have candida infection. Then later on, in HIV Class 3, you first start having tuberculosis. Is it clear? In HIV Class 3, you can have systemic herpes infection still in HIV Class 3. You can have systemic candida infection still in HIV Class 3. Is it clear? Now, when entering now still in HIV Class 3, you can still have cryptococcosis. Is it clear? Because at that level you still have this. Because let me first divide the HIV classes based on the CD4 count. You need to know that what HIV Class 1, the CD4 count is going to be greater than 500 cells per microliter. Is it clear? In HIV Class 1, the CD4 count is greater than 500 cells per microliter. In HIV Class 2, the CD4 cell count is between 300 to 500. Is it clear? In HIV Class 3, it is between 100 to 300. And then in HIV Class 4, it is less than 100. So let's start with HIV Class 1. HIV Class 1, you need to be greater than 500. To be greater than 500, you see that the level of herpes virus and candida infection in HIV Class 1. In HIV Class 2, it is tuberculosis. Is it clear? So it's going to be in HIV Class 2, you are going to have level of tuberculosis. You have also systemic herpes infection, systemic candida infection. You can also have cryptococcus infection. Is it clear? You also have cryptococcus infection in still HIV Class 2. Is it clear? Now, still in HIV, so now you need to know that what, because HIV Class 2 was ending at the level of of 300. It was between 500 to 300. So Cryptococcus can enter HIV class 2 or HIV class 3, but it's better to classify Cryptococcus in HIV class 3 than HIV class 2. Is it clear? Now, this is the Pneumocystis jirovecii infection. Is it clear? Pneumocystis jirovecii infection enters into HIV class 3 with Cryptococcosis. So Cryptococcosis, Pneumocystis jirovecii infection, you see that by this level you are between 100 to 300. This HIV class 3 Cryptococcosis and Pneumocystis jirovecii infection. Then later on, now when you are less than 100, you have things like toxoplasmosis, you have things like cytomegalovirus retinitis, and you have things like disseminated carcinomas, is it clear? Malignancies, is it clear? Associated with AIDS. So what are the disseminated malignancies associated with AIDS? We have the first one is Kaposi sarcoma, the second one is lymphoma, the third one is cervical cancer. Kaposi sarcoma, the major cause is going to be human herpes type A. The next one is cervical cancer. So you have that is for, so those are the HIV associated carcinoma. We say Kaposi sarcoma, which is caused by human herpes class 3, human herpes 8, human herpes virus 8. You have cervical cancer, lymphoma, which is directly caused by HIV, or it can also be caused by human T lymphotrophic virus type 1 and type 2. And we have also cervical carcinoma, which is caused by the human papilloma virus type 16 and type 18. So this is the herpes virus 8 viridium, which is the cause of Kaposi sarcoma, which can be seen here. Now, what are the currently available drugs? Is it clear? The currently available drugs for HIV to do the highly active antiretroviral therapy. You need to know that there are nucleoside and nucleotide reverse transcriptase inhibitors. The nucleoside and nucleotide reverse transcriptase inhibitor, you have abacavir, you have didanosine, you have M3-citabine, you have Laminate Region. You have also stavudine, tenofovir, zidovudine. Now, the non-nucleoside reverse transcriptase inhibitor, you have efavirenz, you have nevirapine, etravirine, and you have delavirine. The protease inhibitor, in case of the protease inhibitor, is finishing with OV, viritanovir, indinavir, so it's finished with navir, indinavir, tiva, tipronavir. All these navies are the one involved with protease inhibitor. Now, the entry inhibitor, you have enfuvirtide. Enfuvirtide is the one that inhibits the entry of the HIV into the cell. Integrase inhibitor, we have raltegravir. We have also the CCR antagonist, the maraviroc. And now we have the combination therapy. So you need to know that when you want to do highly antiretroviral therapy, you do a combination of these drugs here. And the combination, you can use 2 nucleoside or nucleotide reverse transcriptase inhibitor. So use 2 of them. So when you want to do a combination to produce a highly active antiretroviral therapy, you combine the combination as such here. You can do 2 nucleoside or nucleotide reverse transcriptase inhibitor plus 1 protease inhibitor plus, or you do a nucleoside reverse transcriptase inhibitor or integrase inhibitor. Is it clear? So you do 2 nucleoside reverse transcriptase inhibitor plus 1 protease inhibitor, or you can do plus 1 nucleoside non-nucleoside inhibitor reverse transcriptase inhibitor plus an integrase inhibitor. Is it clear? So let's take the combination that we do in Cameroon. The combination that we do in Cameroon is tenofovir, lamivudine, efavirenz. That's the first combination that we do in Cameroon. Tenofovir, lamivudine, efavirenz. Now, what is tenofovir? As you can see in this diagram here, tenofovir is a nucleoside or nucleotide reverse transcriptase inhibitor, so it's among them. Is it clear? Now, the second is Lamivudine. What is Lamivudine? Is nucleoside or reverse transcription inhibitor. So that's why it respects 2 nucleoside or nucleotide reverse transcription inhibitor. That's the first part of the combination. Now, the next is efavirenz in Cameroon. In efavirenz is, so we use efavirenz also in Cameroon. Efavirenz is this one. So as you can see the efavirenz. Is it clear? And efavirenz is a non-nucleoside reverse transcription inhibitor. Is it clear? And that's why in the combination you can also use a non-nucleoside reverse transcription inhibitor. Is it clear? Now there's another combination. If you fail with the first line, you can go to the second line of highly antiretroviral therapy. Usually in antiretroviral therapy in Cameroon, we never remove lamivudine. So in second line we use zidovudine, lamivudine, and nevirapine or efavirenz. Is it clear? So zidovudine is still a nucleoside, lamivudine is still a nucleoside, and then there is efavirenz, or we can put nevirapine. Is it clear? Now there is also another one which is abacavi. Abacavi can also be used, and abacavi is among the nucleoside and nucleotide. If you don't want to use zidovudine, you can use also abacavi. Is it clear? So generally, if you want, in Cameroon we always maintain lamivudine, but we can change and place any other nucleoside or reverse transcription inhibitor, just as you can change tenofovir with zidovudine or abacavi. Is it clear? And when we want to change the non-nucleoside reverse transcription inhibitor, we can change and we put nevirapine, or we put efavirenz. Is it clear? But there are certain cases where we can completely remove the non-nucleoside reverse transcription inhibitor and place the protease inhibitor, such as ritonavir. Is it clear? Ritonavir is the major one that we use. Ritonavir. Is it clear? And it is very rare that we use integrase inhibitor, such as raltegravir. So that is highly active antiretroviral therapy. So what are the role of immunodeficiency virus protease in viral reproduction? So what happens in immunodeficiency is the viral penetrates. You are going to have viral DNA, and it's going to take the host mechanism of the virus cell. And what happens is that the viral RNA, you have the gap pull and all that, as the virion bud from the surface, the viral protease is activated and cleave the polyprotein into the component protein, which is then assembled into mature virion. The protease inhibitor prevent essential step in virus mutation. So this is how the protease inhibitor works, such as ritonavir. Is it clear? So that's an example of protease inhibitor. The case of penetration. In the case of penetration, we have this. We have the case of the entry inhibitor, such as L-Victa, which is not generally too much used in our context, and also the CCR antagonist. So this is how the entry inhibitor can be used here. The one that are able to prevent the reverse transcription from acting are capable to be used here. The reverse transcription inhibitors are going to be used here. Both the nucleoside, nucleotide, non-nucleotide are going to be used here. And we have also the integrase inhibitor also be raltegravir can be used at this step, and you have also the protease inhibitor which can be used at this step. Now, what is the incidence of opportunistic infection in patients with HIV? Now, we need to know that what generally opportunistic infection, we said there is the cases. You need to know that based on the years, before it was toxoplasmosis were high, but now it has highly reduced, because we have understood highly the pathogenesis of toxoplasmosis. Now we have also cytomegalovirus retinitis, which occur in class type 4 HIV, class 4 HIV. So it's also there. We have Mycobacterium tuberculosis occurring in class 3 HIV. Is highly depreciating by the time of 1996, when the combination therapy for when the heart has been initialized. You see, by this time the heart has been initialized. Is it clear? So, and also the pneumocystis jirovecii has highly reduced when the heart has been initialized. Is it clear? Now, The next one is the human T-cell lymphotrophic virus type 1 and type 2. Is it clear? It's so highly associated with the adult T-cell leukemia. So the age, incidence, the age and the sex specific of the human T-cell lymphotrophic, you need to know that by this age it is more in females, more in females, more in females. So most of it is going to be more in females compared to the males. Is it clear? So from here we are finished with the Retroviridae family and the AIDS. We say thanks for your kind attention, and don't forget to like and subscribe for our channel, Science Video Maker. Thank you.